In this video, we are going to discuss another problem from Bmath 2008, and that is problem number 8. So, the problem says that you have a squared plus b squared is equals to 1, c squared plus d squared is equals to 1, and ac plus bd is equals to 0. And you have to prove that a squared plus c squared is equals to 1, b squared plus d squared is equals to 1, and ab plus cd is equals to 0. But nothing has been given about abcd. So if you are considering that abcd is real and using some trigonometric identities, so be careful that you haven't been told that abcd are any real numbers. So now let's proceed. So if you notice that if you multiply this matrix A, or let's say capital A is equals to A, B, C, D. Okay, so let me multiply this matrix A, B, C, D with its transpose, that is A, D, C, B. Then what are you getting? So a square plus b square, and then ac plus bd. Here also you are getting ac plus bd, and here you are getting c square plus d square. And now notice that, so this is a times a transpose. Now what is transpose? Basically, transpose of a matrix is the ijth position, whatever that element is, it goes to the jith position, and jith position element comes to the ijth position. And since the diagonal entries like the where I equals j, so for those elements it doesn't matter. So now you see that here a square plus b square, c square plus d square, they are given to be 1, and ac plus bd is 0. So this basically boils down to 1 1 0 0. So the identity matrix. Okay, so a transpose is equals to the identity matrix. So this is a very special type of matrix. So then we say that A is orthogonal. So A is an orthogonal matrix. Okay. So now for the orthogonal matrix, there are some certain, very nice properties. Like you can prove that the orthogonal matrix, their determinant is non-zero. So why? Because you see that A transpose is equals to identity. Okay, so so suppose it's n cross n identity. Okay, that's why I'm writing in. So then if I use the determinant function on both the sides, then I get determinant of A times A transpose is equals to determinant of in and which is equals to 1. So the determinant is basically a function which takes matrices to the real numbers. So now what we have is, so and also determinant is a multiplicative function. So determinant of A times determinant of A transpose, which is equals to 1. Okay, and now determinant of A transpose is the same as determinant of A, and so this basically boils down to determinant of A whole square is equals to 1, and which implies that determinant of A is equal to plus or minus 1. And this is a very nice property of the orthogonal matrices. Now so the orthogonal matrices have to be square matrices. Now what do we get from here? So we get that any orthogonal matrix is invertible. So now why do we need that? So let's come to the thing that we have to basically prove. So let me just go above. Now you see that A transpose is this, but what about A transpose A? So A transpose A. So that is, you have A was A, B, C, D. So A transpose would be AD, CB. And how much is this? If you are multiplying, so it's A squared plus C squared, and then A is AB, CB, CD, AB plus CD, and here AB plus CD, and then B squared plus D squared. Okay, so this is what we have to prove, that is, this is the identity matrix we have to prove, because you see that we have to prove A squared plus C squared is equals to 1, B squared plus D squared equals 1, and AB plus CD is equals to 0. So basically this problem is nothing but they are asking you that if A transpose is equal to identity, then prove that A transpose A is also identity. Okay, that is what they are asking you to prove. So we have to prove that this is identity. Now what has been given to us, that is A transpose is equals to the identity. Okay, identity matrix I mean. Now okay, now I have to go to A transpose A. So for that what I can do is I need A transpose A. So I'll just multiply A on the right hand side. So A transpose A. So this matrix multiplied with A basically. So you're getting I times A, which is A itself, or also you can say that it's equal to AI. Okay, so now matrix multiplication is associative, so we can say that A transpose A is equal to AI. Okay, I wrote I times A, the identity matrix multiplied by multiplying with A. So it basically means nothing, like if you are writing it's equal to AI, so because of the identity matrix. So that doesn't happen for any matrix. So that is basically the commutative property which doesn't hold in the set of matrices. Okay, so you can have two matrices where AB might not be equal to BA. Okay, so now let's take everything on one side. So I can take the A common, and I am having A transpose A minus identity is equals to, now don't just write 0, so it doesn't make sense because the whole equation is involving matrices. So let's write big O to denote that it's a matrix, 0 matrix. Okay, so this is the 0 matrix. Clear? Now we see that what do we have to prove? A transpose A is equals to identity. We have A transpose is equals to identity. We have this, but we have to prove that A transpose is equals to identity, and so we have to prove that this part. So the product, I have the product of two matrices, and that matrix will be the 0 matrix, because then only A transpose A will be identity. So now what I can do is, since I just proved that the determinant of any orthogonal matrix, A is an orthogonal matrix because it's given that A transpose is equals to identity. So since the determinant is non-zero, so I can invert it, and yeah, and orthogonal matrices are square matrices. And in our example we don't have to care because it's already a 2 cross 2 matrix, which is a square one. So yeah, it's invertible. Okay, and so I can just multiply by A inverse on both the sides. So A inverse A transpose A minus I is equals to A inverse times the zero matrix, and which is again the zero matrix, and that is A inverse A becomes the identity matrix I, A transpose A minus I. Okay, so if you are proving this in general, let's take I to be any, or in our situation A is 2 cross 2, so let's take 2. Okay, so this proof can also be done for just for any n cross n matrix. Okay, so yeah, or you can separately write that I is the identity matrix of order 2 cross 2. Okay, so this is equals to the zero matrix, and now what? So we have identity times some matrix. So this is also a matrix, right, after all. So this matrix times identity times this matrix would be again the same matrix. So A transpose A minus I2 is equals to the zero matrix, and that implies A transpose A is minus I2 is equals to the zero matrix. Oh, sorry. Yeah, so let's take I2 on the other side. Yeah. So I2, and what does this imply? That is A transpose A is equals to the identity. So what we required here. So now A transpose A here, this is the identity matrix 1 1 0 0, and so if you are comparing component wise, so A squared plus C squared is equals to 1, B squared plus D squared is equals to 1, and AB plus CD is equals to 0. Okay, and so we are done proving what was given here. So A squared plus C squared 1, B squared plus D squared is equals to 1, and AB plus CD is equals to 1. Okay, so yeah, that's it for today. So we'll meet in the next video. So hope you liked it. Thanks for watching. Bye.